Hello and welcome students. We are starting with a new topic by name indefinite integration. Now when I say indefinite integration, the question could be why the name indefinite? So we have to understand why we say indefinite, and we will also understand the meaning of integration. We have already covered in the previous topic, we have covered differentiation. That is, we have studied how to differentiate a function of x, how to differentiate a function of x with respect to x. This we have studied in the previous topic, how to differentiate a function of x with respect to x. If you have not studied this, then you watch the previous videos. Now when I say to differentiate a function of x with respect to x, I mean d by dx of f of x. I mean d by dx of f of x. So I mean d by dx of f of x. So if this is known as derivative, if this is known as derivative of f of x with respect to x, then what would be the meaning of integration of f of x with respect to x? So in our today's agenda, this is something that we would like to know. What is meaning of integration of, the meaning of this? Okay, integration of f of x with respect to x. So let's go ahead. See students, consider two real functions of x, real valued functions of x, f of x and g of x, such that d by dx of f of x equals to g of x, such that d by dx of f of x is equal to g of x. Now this is something very common. You have two functions of x and you notice that derivative of one of those with respect to x is the other, and this is something very common. Suppose I have sin x and cos x. So you all know d by dx of sin x is equal to cos x. So here, whatever I have written here, there is nothing rocket science as such. Whatever I wrote here, it's very simple thing. So you can take this as f of x and this is g of x. Derivative of f of x with respect to x is g of x. So here I consider two functions of x, f of x and g of x, such that d by dx of f of x is g of x. Then I can write here something. Here I will write something. Okay, I repeat again. This is true. This is true. Just because this is true, I can write here something. What I am writing, I want you all to see this. Then okay, I wrote here something in the box, but I did not read it. Now I will read it. How to read it? Integral g of x with respect to x equals to f of x. How do I read what I wrote? I read it as integral. See this sign. You see this sign? It is nothing but s. It is nothing but s. But this s, what we are doing is, we are pulling it. We are pulling it upward and downward. Okay. So when you pull that upward and downward, it becomes this, which is known as integral sign. Integral g of x. See, inside we have g of x. And this dx indicates what? It indicates with respect to x. Integral g of x with respect to x equals to f of x. So what you followed here? What did you follow, students? You followed that if I have two functions of x, if I have two functions of x such that derivative of one of those function is the other function, then integration of the other function will be the previous function. Okay, what is derivative of f of x with respect to x? F of x with respect to x is g of x. Derivative of f of x with respect to x is g of x. Hence, you will say integration of g of x with respect to x will be f of x. I repeat again, learn this. Derivative of this is this. Hence, integration of this will be this. Very simple definition. Very simple definition. This definition we are going to use and write some very important results. Okay. So what did you write? D by dx of f of x is g of x. So integral g of x dx with respect to x. Integral g of x with respect to x is f of x. Derivative of f of x with respect to x is g of x. So integration of g of x with respect to x will be f of x. Okay. Very good. Now here I will write something more to it. I want you all to be very attentive and see here. Yeah, so students, I give you some examples. So following this is definition. What I wrote here can be termed as definition of integration. This is definition. So students, I can say here d by dx of x square is 2x. So can I say from this, can I say integration of 2x with respect to x is x square? Can I say this? Yes, this is correct. Next, d by dx of sine x is equal to cos x. So can I say that integration of cos x with respect to x is sin x? Okay. So what you are thinking is perfectly all right. But then there is a small thing to be added more to this. And what is that small thing? I will let you know. It is, you must have seen that whenever you are integrating, you must have noticed in your other lectures, or maybe in physics you have done a bit, that when you are integrating you add a constant of integration. Now how does that constant of integration come into picture? That you have to understand. So for that I shall give you an example. See, if I write here d by dx of x square, so d by dx of x square is 2x. Now when I apply the definition of integration on this, I get integration of 2x with respect to x is x square. Derivative of this is this. So integration of this will be this. Very simple. Very simple. So here I have, then next I write is d by dx of x square plus 10. So you all know, students, if I'm writing d by dx of x square plus 10, it will be d by dx of x square plus d by dx of 10. Now d by dx of x square is 2x and d by dx of 10 is 0. So here I have 2x. d by dx of x square plus 10 is 2x. So I notice that I apply the definition of integration on this and I will get integral 2x dx is equal to x square plus 10. You get it as x square plus 10. So if I write next as d by dx of x square plus 100, it will again be 2x, because every time you differentiate a constant, derivative of constant is 0. So d by dx of x square plus 100 is 2x. This gets me integration of 2x dx is equal to x square plus 100. I'm applying the definition of integration, which says derivative of this is this. So integration of this will be this. Okay. This way, if I continue ahead, no matter how big a constant I add with x square plus 1000, the derivative again is 2x. And when I apply the definition of integration, I will get integration of 2x dx is equal to x square plus 1000. Now from this you all must have understood, students. It is very important for you to understand here that you all to understand here that when you are differentiating x square, you got 2x. When you differentiated x square plus 10, you got 2x. So every single time when you are differentiating a function, you get a unique function. It is very important. I repeat once again, I want you all to understand. Okay, suppose I make a set. Try to understand what I'm trying to teach you all. This is very important and you all should try to understand this. It is very important. You should all try to understand this. Suppose in this set I write the functions x square plus 10, x square plus 100, x square plus 1000, x square plus 10,000, x square plus any number I write, whatever constant I write here. Okay, it has to be a constant. And suppose in this I have the derivative. Okay, what do I have? I have derivative. So derivative of x square, what is derivative of x square? Derivative of x square, you will note that it is 2x. Derivative of x square is 2x. If I ask you how many derivatives d by dx, okay, so from here to here, what is happening? when you are writing, when you are associating a member of this set from this set, it has gone through d by dx. Okay. So what is happening? This is differentiated with respect to x before putting in this set. So if I ask you derivative of x square with respect to x, it is 2x. And then I ask you, how many derivatives do you think x square will have with respect to x? Remember students, it is one and only one derivative which x square will have. It is a single derivative. X square has just unique derivative as 2x. It cannot have any other derivative than 2x. Then it is x square plus 10. What is derivative of x square plus 10 with respect to x? 2x. X square plus 100, 2x. X square plus 1000, x square plus any number, it is always 2x. What I am trying to tell you is, when you are differentiating a function, remember, when you are differentiating a function, the derivative of a function is always unique. X square has one and one derivative, that is 2x. This also has one and only one derivative, that is 2x. So these all functions have single derivatives. Okay. When you are differentiating a function, you are sure that you are going to get a unique function. X square has derivative 2x, that's it. X square plus 10 has two derivative. X square has just one derivative, 2x. X square plus 10 has one derivative, 2x. X square plus any number has just one derivative, 2x. It is always unique. But now I want you all to see the other part, that is after this implication sign. I want you all to see this part. Okay. See here what's happening. You notice integration of 2x with respect to x is x square. In the first one you notice this. In the second one you notice, though it is same function 2x, here you integrated 2x, here also you are integrating 2x. This is also integration of 2x, this is also integration of 2x. You notice that all these functions which you are integrating is one and only one, 2x. But on the right you notice that integration of 2x is x square. Integration of 2x, here it is x square plus 10. Integration of 2x is x square plus 100. It is x square plus 1000. So if I go for integration, what I notice that integration of a function is not unique. Integration of a function is not unique. Why? See, integration of 2x is x square. Integration of 2x is x square. Integration of 2x is also x square plus 10. It is x square plus 100. It is x square plus 1000. It is x square plus whatever number. So integration of a number is not unique. What I said integration of a function is not unique. The integration of a function is changing. How is that changing, students? Here, when you are integrating 2x, you added 0, x square plus 0. Here it is x square plus 10, x square plus 100, x square plus 1000. So you notice that every single time the integration of a function is changing, and it is changing with what? In what? It is changing in the constant part. See, it is changing in constant part. So if you are if you have a question that why is this constant changing, I would like to tell you that you check the earlier part of it. Here you wrote integration of 2x as x square plus 10 because it was x square plus 10 whose derivative was 2x. And here you are writing integration of 2x as x square plus 1000 because it is x square plus 1000 whose derivative of 2x. So if somebody asks me what is integration of 2x, if somebody asks me what is integration of 2x, I know students that x square will definitely be there. X square is every time there. You check this, x square is every time there. And then after that I write plus c. Why do I write plus c? because this c can be any number. It can be any finite number. It can be any finite number. So now I have explained you that why do we add a constant when we are integrating. When we are integrating, why do we add constant? Because addition of constant completes the definition. Addition of this constant completes the definition. What is this constant known as? This constant is known as constant of integration. It is constant of integration. I hope that whatever I'm writing, you all keep writing it. Okay, this is known as constant of integration. If at all you have a doubt whether this is correct or not, okay, integration of 2x is x square plus c. So if you have a doubt, you can just do one thing. You differentiate x square plus c. So d by dx of x square plus c. Now check what it will be. It will be d by dx of x square plus d by dx of c. D by dx of x square is 2x and constant derivative is 0. So you have 2x. So what do you say? You say that d by dx of x square plus c is 2x. Derivative of x square plus c is 2x. So if derivative of this is this, integration of this is this. 2x is x square plus c. I hope you all have understood this. Now let's move ahead. So what I will do now, I will now write the complete definition. Okay, whatever I had written earlier, I will write that definition once again. Okay, and I want you all to copy this. Consider two real valued functions f of x and g of x such that d by dx of f of x is equal to g of x, such that d by dx of f of x is equal to g of x. Then we can write what you can write. Then you can write integral g of x with respect to x is equal to f of x plus c. What have you written, students? Integral g of x dx is f of x plus c. What did you do? You added c. Derivative of f of x with respect to x is g of x. So integration of g of x will be f of x plus c. This constant is always added. Then I hope you have written this. Now using this definition, we are going to write some important results, and these important results you will all copy as I go ahead. So I write here some important results. So let's go ahead. The first one is d by dx of sin x equals to cos x. This implies integral cos x dx equals to sin x plus c. Integral cos x dx is sin x plus c. Then second, d by dx of cos x is equal to minus sin x. Okay. Now students, derivative of cos x with respect to x is minus sin x. So if I continue with this, I will get integration of minus sin x. You see this? I will get integration of minus sin x. But I don't want integration of negative of sin x. I want integration of sin x. I want integration of sin x. So for that, what I do is, see, I write derivative of minus cos x. So if I differentiate minus cos x, what will happen? This minus will be -1, it will be out, and derivative of cos x is minus sin x. So here you will get plus. I hope this is clear. If you are differentiating minus cos x, you will get sin x. D by dx of minus cos x is sin x. So here integration of sin x dx is equal to minus cos x plus c. It is minus cos x plus c. Then the third one. Third is d by dx of tan x equals to sec square x. This implies integration of sec square x dx is equal to tan x plus c. Every time you add c, and why you add c, this I have already explained. Fourth, d by dx of sec x is sec x into tan x. So this gives us integration of sec x tan x dx equals to sec x plus c. Fifth, d by dx of cosec x is negative cosec x cot x. But you know, students, if I have negative and which I do not want, I will have to put a negative sign here. So if I write d by dx of negative cosec x cot x, then definitely here I will not get cosec x cot x negative. So d by dx of negative cosec x cot x is cosec x cot x. This gets me integration of cosec x into cot x dx equals to minus cosec x plus c. Sixth is d by dx of cot x. You all know it is minus cosec square x. So if I put a negative sign here, I will get positive cosec square x. So this gets me, I apply, what am I doing every time? Students, I am applying the definition of integration. What I am doing? I am applying definition of integration. Derivative of negative cot x with respect to x is cosec square x. So integration of cosec square x with respect to x is negative cot x plus c. Okay. These are 6 trigonometric functions whose integration I got. Now, there is something which I would like to make a note of and see what it is. Students, when we did the topic of derivative, there we differentiated sin x, cos x, tan x, sec x, cosec x, and cot x. So what I want you all to note here is, in topic of derivative, when you started, you had in your hand derivative of 6 standard trigonometric functions. But in this integration topic, you notice right now, as of now, that is, today is the first lecture. So in the first lecture, you have derivative of integration of cos x, integration of sin x, but where is integration of tan x? See, you are not having integration of tan x. As of now, integration of tan x you are not having. Integration of cot x you are not having. Integration of cosec x you are not having. Sec x you don't have integration as of now. So instead of all these, you have some very different unique functions whose integration you have, and that is integration of sec square, integration of sec x tan x, integration of cosec cot x, integration of cosec square. So what I want to tell you is that integration of those four functions like tan x, sec x, cosec x, cot x, it will come in lecture to come. In next lecture you will see integration of these functions. Right now what you have is integration of trigonometric functions, which are like sec square, sec x tan x, cosec x cot x, cosec square x. But if you have a doubt in your mind that why are we getting integration of such a function, remember students, you are getting integration of this function because this is derivative of tan x. Why are you getting integration of sec square x here? Because sec square x is derivative of tan x. It is derivative of tan x. So integration of sec square will be tan x. Sec x tan x is derivative of sec x. Cosec x cot x is derivative of negative cosec x. I hope it is clear. So these functions you will try to remember. Right now, which trigonometric functions you integrated? So you have integrated total 6 trigonometric functions as of now. And those are, first one is cos x, second is sin x, then sec square x, then sec x tan x, cosec x cot x, and cosec square x. Okay, now we move ahead and write some more functions and their integrations. So now seventh one is, see here, I write the seventh as, see, I write here integration of, I'm sorry, I have to start with derivative. See, we know that d by dx of x raised to n. What is d by dx of x raised to n? It is n into x raised to n minus 1. Now when I apply the integration definition on this, when I apply the definition of integration, I will get integration of n x raised to n minus 1 dx. I will get integration of this. See, I'm writing derivative of this, which is this. So definitely I will get integration of this only. Okay. But the thing is, I'm not interested in integration of any such looking function. I want integration of a standard function. Like here, you wrote derivative of x raised to n, which is variable raised to constant function. It is variable raised to constant function in its very basic form. Whereas integration, when you are writing, you have variable raised to constant, but that constant is not n, it is n minus 1. Moreover, there is one n multiplied here. So this is not solving our purpose. Okay. So what we do is we discard this and we do something different. What different do we do? You will notice it within a minute. See here, I begin it this way. I write d by dx of x raised to n plus 1 upon n plus 1. d by dx of x raised to n plus 1 upon n plus 1. So what will happen next, my dear students? This I'm differentiating with respect to x. So if I have anything which is not x, then it is a constant. So here n plus 1 in the denominator will be treated as a constant. So you have 1 upon n plus 1 out. And here you have d by dx of x raised to n plus 1. You have d by dx of x raised to n plus 1. So the next step, you have 1 upon n plus 1. And here I differentiate this with respect to x, which is variable raised to constant. So its derivative will be n plus 1 x raised to n plus 1 minus 1. Okay, the next step, you know very well what will happen. This n plus 1 will cancel, and here plus 1 minus 1 is 0, so you get x raised to n. So what you got? You got d by dx of x raised to n plus 1 upon n plus 1 is x raised to n. D by dx of x raised to n plus 1 upon n plus 1 is x raised to n. So here now I apply the definition of integration. So if derivative of this thing is here, so what I can write, my dear students, I can write here, therefore this implies integration of x raised to n dx. Integration of x raised to n dx is equal to x raised to n plus 1 upon n plus 1 plus c. And here I will make a note where n is, I must write a note here, where n is not equal to minus 1. Remember students that when you are writing this result, n is not minus 1. N is not equal to minus 1. Okay, very good. So this is integration of x raised to n. What is integration of x raised to n? It is x raised to n plus 1 upon n plus 1. Okay. Okay, so students, you got the integration of variable raised to constant. Now we have eighth. Eighth is d by dx of a raised to x, which is constant raised to variable. You know, integration of a raised to x is, sorry, derivative of a raised to x is a raised to x, a raised to x into log of a. What is derivative of a raised to x? It is a raised to x into log of a. So if I go ahead and I apply the integration definition, I would be getting integration of a raised to x into log a. Okay, now a raised to x into log a, if I write the integration, it would not be considered as integration of a standard function. Integration of a raised to x log a dx I will get, which will be a raised to x plus c. Okay, so it would not be considered as a integration of a standard function. So what should I do here? I should try to write integration of a standard function. For that, what I do here, see students, I write d by dx of a raised to x upon log a. Okay, I start differentiating a raised to x upon log a. Now next what happens is this 1 upon log a is a constant. A constant, see, a constant means something which is devoid of x, which does not have x in this. So here when you are differentiating with respect to x, and inside this when you do not have something in x, so that is definitely a constant. So 1 upon log a is constant, and here I have d by dx of a raised to x. Okay, so here then, so d by dx of, so you will get d by dx of a raised to x upon log a will be 1 upon log a into d by dx of a raised to x, which is a raised to x log a. And what will happen? This log a cancels. So you get therefore d by dx of a raised to x upon log a equals to a raised to x. See, you are left with a raised to x only. So here I shall apply the definition of integration, and that will get me, see, derivative of this with respect to x is this. So integration of a raised to x dx is a raised to x upon log a plus c. Okay, this is 8th. I got integration of a raised to x, and in 7th I got integration of x raised to n. Then next I will do integration of, see, now it is 9th. I write d by dx of e raised to x. You know, d by dx of e raised to x is e raised to x. So this implies integration of e raised to x with respect to x is also e raised to x plus c. E raised to x plus c. I hope you all are copying this. And if you all are not copying it, you can just pause the video later and copy it. It is always better that you go along with the teacher. When you are watching the video, at that time only you should keep writing this. That will save a lot of time of yours. So students, in the previous page, I taught you up to integration of e raised to x. Then I go ahead. The 10th one I take is, d by dx of log of x. What is this equal to? It is equal to 1 upon x. So when I apply the constant, if I apply the definition of integration here, I will get integration of 1 upon x dx equals to log of x plus c. What I will get, students? I will get integration of 1 upon x dx is equal to log of x. But one thing I would like to tell you all students here, that derivative, when you are writing d by dx of log x, remember students that this x is greater than 0. This x is greater than 0. This is very important. You should know it. And those who do not know it, they should make a note of it. When you wrote d by dx of log of x as 1 upon x, then this x here is greater than 0. Why? Because log of negative is not defined. Log of 0 is not defined. Okay? So remember, if you consider only this part, which I enclosed in the red color, if you consider only this part, d by dx of log x is 1 by x, what is happening? The x is greater than 0. But now come to the right side. Now here I'm having integration of 1 upon x. Students, 1 upon x is a function. 1 upon x is a function which is defined for x positive as well as x negative. 1 upon x is not defined for x0. It is not defined for x0. That is why you write x not equal to 0 when you write 1 upon x. I repeat once again what I'm trying to say. Students, when you are writing the function 1 upon x, remember that 1 upon x, here you can substitute x positive. You can substitute x positive. You can substitute x negative. You can substitute x negative. The only thing that you cannot substitute here is 0. You cannot substitute 0. 1 upon x is not defined for x equal to 0, because if you write 0 here, then it is not defined. 1 upon 0 is not defined. 0 in the denominator is not defined. So if you are thinking that why am I telling you all this? Why am I telling you all this? I'm telling you this all because this whole thing which you wrote here, in this, x is positive. Here x is positive. Why? Because when you started here writing d by dx of log of x, there itself in the beginning x was positive. So everywhere x is positive. So there can be always a question, there can always be a question that you wrote integration of 1 upon x, x is positive. Here this x is positive. What about integration of 1 upon x when x is negative? What about that x when x is negative? Because anybody can question 1 upon x is defined even for negative x. So this, when I'm writing, it is not getting me the clear integration. It is not getting me the complete integration of 1 upon x. If you write integration of 1 upon x as log of x, it is only integration of positive x in 1 upon x. So what should I do for that? I will tell you. See, so we will have here cases. We will have here some cases. Okay, so as I told you all that when we are differentiating log of x, this x is always positive. So here I will have two cases. See, the first case is, I will write here case 1, and in case 1 I write x greater than 0, and then I write d by dx of log of x equals to 1 upon x. You know log of x, and x is greater than 0. So applying the definition of integration, I will get 1 upon x integration of 1 upon x dx is log of x plus c. Then I go for the second case. The second case is, I write here case 2. And case 2 is x is lesser than 0. Students, when I'm writing x less than 0, then remember students, I cannot write d by dx of log x. This is very important. I want you all to be very attentive. When I wrote x greater than 0, I wrote log of x, which is correct because x has to be positive when you are writing log. Log of negative is not defined. But when you wrote x less than 0, you cannot write log of x. So what I will do is, students see, I will write log of minus x. Now it is perfect. Now this is perfect. I'm writing log of minus x. Now how it is perfect? It is because x is lesser than 0. So when you write negative of x will become greater than 0. If x is less than 0, then minus of x will be definitely greater than 0. I hope you followed it. Minus of x will be greater than 0. So here, now I differentiate d by dx of log minus x. What it will be? As you know, students, this is now log function. This is log function, but the variable of this function is not matching with this. See, it is log of f of x because it is minus x, whereas you are differentiating with respect to x. So its derivative will be 1 upon minus x into d by dx of minus x, which is minus 1. So you get here d by dx of log of minus x is equal to, this minus and minus cancels, 1 upon x. So I notice that d by dx of log of minus x is also 1 upon x. So this implies I get, now I apply the definition of integration. I get integral of 1 upon x dx is equal to log of minus x plus c. So the next point is, I will now combine these two. Students, see what I will do. I shall now combine these two. I will combine case 1 with case 2. Okay, what does case 1 say? It says integration of 1 upon x is log of x when x is positive, and integration of 1 upon x is log of minus x when x is negative. So when I combine these two, what it will become finally, that I will write for you. See, it will become so here I write from case 1 and 2, from case 1 and 2 we can write integration of 1 upon x dx is equal to log of mod x plus c. What happened? I noticed that once it is log of x and the second it is log of minus x. So x and minus x, I combined these two and I wrote what? Mod of x. Because I know the definition of mod of x. Mod of x is x for x greater than 0. Mod of x is negative x for x lesser than 0. So mod of x I wrote here. Okay. So please students, you will copy this. You will copy this. And the main result that you have here is this. This is the main result. What is 1 upon x? dx, integral 1 upon x dx is log of mod x plus c. So 10th is done. We go for the 11th one. D by dx of x is equal to 1. You all know d by dx of x is 1. This implies
Sir, sir.
So here we have d by dx of x equals to 1. D by dx of x is 1. I apply the definition of integration. So integration of 1 with respect to x is x plus c. What we have, derivative of x with respect to x is 1. So integration of 1 will be x plus c. So from here we conclude one very important fact. What is it? It is derivative of a constant is 0. Derivative of a constant is 0. Derivative of a constant is 0. But check here, students, you are integrating 1. What is that 1? 1 is a constant. Is integration of constant is 0? No. Integration of a constant is not 0. Integration of a constant is not 0. So now let's go ahead here. Then after this I write 12th. D by dx of root of x. So few of these functions that now I'll be writing 12, 13, 14, they are as such not the main function. They are sub functions. They depend on some other function. But then since they are quite often used, we give them a separate identity and we call them as root function, reciprocal function. So here you have d by dx of root of x. D by dx of root of x is 1 upon 2 root x. So if d by dx of root x is 1 upon 2 root x, this implies integration of 1 upon 2 root x dx will be root x plus c. But students, I'm not happy with this as I'm getting integration of 1 upon 2 root x, as I'm getting this 2 in the denominator, I'm not happy. So what I do is, I write here integration of, see, I write here d by dx of 2 root x. Now you know derivative of 2 root x will be, this 2 will be constant and d by dx of root x. So 2 and d by dx of root x is 1 upon 2 root x. This 2 is gone. So you get 1 upon root x. So you are getting d by dx of 2 root x as root x. So if d by dx of 2 root x is 1 upon root x, this implies integration of 1 upon root x dx is equal to 2 root x plus c. Okay. Remember students, there can be an argument on this. One can argue that if I have to integrate 1 upon root x, why wouldn't I write 1 upon x raised to half? And then I write x raised to minus half and then integrate using x raised to n, which is x raised to n plus 1 upon n plus 1. You understand? There can always be an argue on this, that I will I will integrate 1 upon root x, writing x raised 1 upon x raised to half, and then this will go up x raised to negative half. Then I will apply x raised to n. That is okay, you can do that, but remember that if you do this, it will take about 30 seconds. But if you try a bit more and you take an effort of remembering this 1 upon root x, if you try to take it as a standard function, you get its integration in no time. Integral 1 upon root x dx is equal to 2 root x plus c. What we are doing, we are making it as a standard function. We are making it as a standard function. Okay, after this we go for 13th. 13th is d by dx of 1 upon x. What is d by dx of 1 upon x? Minus 1 upon x square. So if I put a negative sign here, then this will become 1 upon x square. So I will apply the definition of integration, and if d by dx of minus 1 upon x is this, so integration of 1 upon x squared dx is equal to minus 1 upon x plus c. Okay, once again, one can definitely say that I will integrate 1 upon x square by writing x raised to minus 2 dx. I will integrate 1 upon x square by writing x raised to minus 2 dx. Then I will write x raised to minus 2 plus 1 upon minus 2 plus 1 plus c. Then I will get x raised to minus 1 upon minus 1 plus c. That is minus 1 upon x plus c. But then my suggestion is, why do you do this? If you can remember it if you can remember this and you get the answer in no time. So take an effort and try to remember this result as I am giving you all. Okay, so you can copy this also. So this completes the first, this is the first list of 13 standard. This is the first list, students. This list which I give, 13 functions I integrated for you, I will call these 13 functions as the first list. Remember, I will always keep saying in the lectures to come, results from the first list. I will say results from the first list. So whenever I will say this result from the first list, I would mean these 13 results. Okay, very good.